Imagine a tiny speck of salt.
Like maybe the size of a grain of sand.
Yeah, exactly, just floating on the wind, right?
Yeah.
And it settles on a bare industrial pipe. Now, to the naked eye, well, it's nothing.
Completely invisible.
Right. But trap that tiny speck of salt under 16 inches of heavy insulation, add a little bit of trapped condensation, and then heat that pipe to several hundred degrees.
That is a recipe for absolute disaster.
It really is.
Yeah.
Because over time, that invisible grain of salt is going to eat this microscopic trench right into the metal. And eventually, it causes a massive 44-inch industrial pipeline to just violently rupture.
Which is terrifying to even think about.
Truly. And today, we are looking at the legal and engineering instruction manual designed to stop that exact disaster from ever happening. Welcome to today's deep dive. Whether you are prepping for some massive project management meeting or you're just insanely curious about how mega infrastructure works, we are decoding a document that usually stays locked away in corporate filing cabinets.
Oh, yeah. You do not see these out in the wild very often.
No, you don't. We're looking at a scope of work for hot insulation works. Specifically, SOW-I001 Revision 0, and this is dated May 18th, 2026.
It is a phenomenal piece of forensic engineering, but it's entirely wrapped in this strict legal framework. This document operates under the 2017 FIDC Red Book.
Right, the Red Book.
Yeah. And for anyone listening who, doesn't spend their days reading international construction law.
Which I assume is most of you.
Right. Fair enough. The FID's Red Book is basically the global gold standard for infrastructure contracts where the employer provides the design and the contractor just executes it.
Meaning they don't get to, get creative on site.
Oh, absolutely not. The contractor doesn't get to improvise at all. Every single millimeter of specification in this document is a strict command. It dictates the risk, the responsibility, and the exact execution.
Okay, let's unpack this. Because reading through this, you quickly realize this isn't just dry legal paperwork.
Not at all.
It is the ultimate instruction manual for taming extreme thermal energy in these mega projects. I mean, the contract covers everything from tiny quarter-inch instrument pipes all the way up to those massive 44-inch main lines we mentioned.
Yeah, the scale is wild.
It is. And the insulation thickness required. That ranges from a modest 25 millimeters for the small lines all the way up to over 400 millimeters for the extreme temperature systems.
Which, that is an astonishing amount of material. I mean, 400 millimeters is about 16 inches of pure thermal resistance bolted onto the outside of a steel pipe.
It's huge.
Yeah. And the engineering challenge here is that the insulation has to maintain the internal temperature of these highly pressurized process fluids or even liquefied natural gas, while simultaneously preventing the ambient environment from interacting with the pipe at all.
To put that 400 millimeter thickness into perspective for you, my first thought was that it's like putting 5 high-tech puffer jackets onto a skyscraper.
That's a great visual.
But the more I read, I realized, a puffer jacket is soft.
Right.
It's compressible. The materials dictated in this document are exotic, they're rigid, and they are highly specialized.
Right.
Like the pink fiberglass you go buy at the hardware store for your attic.
Yeah.
That would probably melt or just disintegrate in this environment.
Or it would be gone in seconds. What's fascinating here is the underlying physics of the materials they actually demand. They aren't just using one type of insulation for everything.
Right. It's super targeted.
Exactly.
Yeah.
They deploy specific materials to solve specific thermodynamic problems. So, for instance, the document mandates expanded perlite for very high temperature applications.
Expanded perlite, what exactly is that?
So perlite is essentially volcanic glass. And what they do is they heat it up until it pops and expands.
Kind of like popcorn.
Yeah, exactly like popcorn. And that process creates millions of tiny air pockets inside the glass, so it can withstand massive heat without degrading, but it stays lightweight.
Wow. Okay, and then they bring in cellular glass for areas where moisture resistance is the top priority, right?
Yeah. Yes.
But how does cellular glass actually work? Because I don't know, glass doesn't sound like something that keeps heat in.
Yeah.
Windows are terrible at that.
Yeah, it's a totally fair point. It works through chemical manipulation. They take crushed glass, they mix it with carbon, and then they bake it.
Just bake it in an oven.
Basically, yeah. And as it bakes, the carbon oxidizes and creates these gas bubbles, puffing the glass up into a rigid foam made of millions of entirely sealed glass cells.
So it's like a foam, but it's glass.
Right. And because the material is fundamentally still glass, it is completely impervious to water. It doesn't wick moisture. It doesn't absorb humidity. and therefore it completely protects the pipe from corrosion while providing real structural strength.
That makes total sense. But what about spaces where you simply don't have room for 16 inches of volcanic rock or glass foam? Because in a massive facility, space is incredibly expensive.
Oh, it's premium real estate.
Right. So if pipes are running right next to each other on a rack, you can't always afford a 400-millimeter jacket.
You definitely can't. And that is where they deploy microporous insulation. This is where the material science gets truly microscopic.
Okay, I love this part.
Yeah, microporous insulation uses particles of silica that are so incredibly small and they're packed so tightly together that the microscopic pockets of air between them are actually smaller than the mean free path of an air molecule.
Wait, meaning the air molecules literally don't have enough physical room to move?
Exactly that. Heat transfers through air when molecules bounce into each other. But if you pack the silica particles so tightly that the air molecules can't collide,
It just can't transfer the heat.
right, you drastically reduce the thermal conductivity. It allows them to achieve massive thermal resistance in a really tiny footprint, saving critical space on those pipe racks.
That is just brilliant. But I want to pivot here and push back on one specific detail regarding the metal itself, because this loops back to the grain of salt we talked about at the very beginning.
Ah, right, the salt.
Yeah. The text zeroes in on a very specific standard, ASTM C533. And it mandates that all these materials must be completely free from chlorides and other leachable silicates.
Yes, it is a strict requirement.
And the stated reason in the text is to prevent, quote, stress corrosion cracking of austenitic stainless steel substrates, unquote.
Oh.
So my question to you is, why does austenitic stainless steel care about salt? I mean, it's called stainless because it's supposed to be impervious to rust, right?
It is highly resistant to traditional rust, yes. But we have to look at what makes it austenitic in the first place.
Okay.
Austenitic refers to the specific crystalline structure of the steel, which they achieve by adding a high percentage of nickel and chromium.
Right, to make it stronger.
Yeah, this molecular lattice makes the steel incredibly tough, highly formable, and capable of handling severe temperature swings without becoming brittle, which is, exactly why they use it for major industrial pipelines.
Big sense.
But that specific crystal lattice has a fatal vulnerability to chloride ions, like the ones found in salt.
So the salt actually attacks the crystal structure directly.
It attacks the passive oxide layer that gives the stainless steel its stainless quality. If you trap condensation under the insulation,
Which happens in humid environments.
all the time, and that water mixes with even trace amounts of chlorides leached from the insulation material, when that happens, it creates a concentrated, highly corrosive microenvironment right against the pipe.
Oh, wow.
Yeah. The chlorides pit the surface. Then, because the pipe is under immense internal pressure and high heat, that mechanical stress actually pulls the microscopic pits apart.
It's tearing itself open.
Exactly. The chloride ions drive deeper into the grain boundaries of the metal, and over time, it slices through the crystalline structure like a microscopic wedge, literally cracking the solid steel from the outside in.
Which means a tiny chemical reaction hidden under 16 inches of high-tech insulation could literally bring down an entire facility.
It absolutely could. And this perfectly illustrates the reality of industrial risk management. By explicitly mandating ASTM C533, the contract is forcing the contractor to apply forensic material science.
They're stopping it before it starts.
Right. They are legally eliminating the chemical precursors to stress corrosion cracking before the first piece of insulation is even purchased.
Okay, so understanding the chemistry is one thing, but that introduces a completely different hurdle, which is the physics of actually putting it on.
The installation.
Because having established these rigid, exotic materials, the text makes it intensely clear that you can't just slap this stuff on the pipe and tape it up.
No duct tape here?
No, definitely not.
Yeah.
The installation requires this rigorous, highly controlled physical choreography.
The physical execution is where theoretical thermodynamics meets the reality of a dirty, busy construction site. Heat always takes the path of least resistance. Always. If you have a seam in your insulation that goes straight down to the hot pipe, the heat will find it. The document calls this a cold bridge, which is essentially a thermodynamic short circuit.
Yeah, I was looking at the installation rules designed to stop those cold bridges, and it is intense.
It's very strict.
Like if the insulation needs to be between 110 and 200 millimeters thick, the contractor has to use a multi-layer application, and they have to stagger the joints.
Right.
But if it gets even thicker, say 200 to 300 millimeters, They have to stagger both the circumferential and the longitudinal joints. It's like extreme bricklaying wrapped around a cylinder.
That's exactly what it is. And if we connect this to the bigger picture, staggering the joints ensures that even if a tiny gap opens up as the pipe expands and contracts, which it will have, the heat only travels a few millimeters before hitting a solid wall of the next layer of insulation.
So it blocks it.
Yeah, it creates a labyrinth that the thermal energy simply cannot navigate.
And it doesn't stop at the straight pipes either. When they get to the valves and the flange joints, they can't just wrap them permanently. The document actually demands purpose-made removable boxes.
Which is driven entirely by maintenance economics.
Really?
How so? Well, valves have moving parts that wear out, right? And flanges have seals that need to be torqued and inspected regularly. If a maintenance crew has to hack through 16 inches of sealed cellular glass just to turn a wrench, it costs the facility a tremendous amount of time.
Not to mention destroying all that expensive material.
Exactly. Worse, when they try to patch that destroyed insulation, the integrity of the wetter seal is usually compromised. So mandating custom-built, latchable, removable housings solves the problem entirely. It allows instant access while maintaining the thermal envelope.
Okay, here's where it gets really interesting. I was reading through the work breakdown structure, the WBS codes, and there's a fascinating contradiction in there.
Oh, I know the one you mean.
Yeah, because this entire document is focused on hot insulation works. It is literally in the title.
Oh.
But then you encounter a specific requirement, WBS item H13518, that explicitly demands personnel protection, cold burn.
Yes.
And it requires rigid PIR or PUR insulation with 316L stainless steel cladding. So my question is, why in the world is a cold burn clause sitting in the middle of a hot insulation contract?
It seems like a glaring typo at first glance, honestly.
It totally does.
But to untangle that, you have to look at what PIR and PUR actually are, and then look at the layout of the facility itself. So PIR stands for polyisocyanure, and PUR is polyurethane.
Okay, so foams.
Yeah, but these are heavily cross-linked chemical foams that cure into a highly dense, physically rigid state. They're essentially impact-resistant thermal armor.
But why are they protecting against the cold if the contract is for hot pipes?
Because modern mega-facilities often process both extremes in close proximity. You might have high-pressure steam in one rack and cryogenic liquefied natural gas in another rack just a few feet away.
Oh, wow. Okay.
And human skin reacts to extreme cold exactly the way it reacts to extreme heat, severe cellular destruction. So the contract acknowledges that human workers have to navigate this labyrinth of extreme temperatures. It mandates these rigid cold burn guards for any pipework or valve assemblies within 2.1 meters of a walking grade or platform.
2.1 meters. So basically anything within vertical arm's reach of a human being standing on a walkway.
Precisely. If a worker slips or leans back or accidentally brushes against a pipe, they aren't touching a freezing cryogenic valve, and they aren't touching a fragile piece of insulation that will crumble under their weight.
Right, they're hitting armor.
Exactly. They're hitting a rigid layer of polymer foam clad in tough 316L stainless steel. It proves the document is engineering the safety of the human workers with the exact same rigor as the efficiency of the pipeline.
That's incredible, which I think perfectly sets up the final puzzle of this deep dive.
The bureaucracy.
Yes, the bureaucracy. We have the exotic chemistry of the materials. We have the meticulous staggered bricklaying of the installation. But how does an employer actually track, manage, and pay for this gargantuan effort without getting scammed?
It is a massive challenge.
Because we were talking about thousands of meters of piping, massive stationary equipment, and a literal army of workers.
Right, and the bureaucracy required to manage this is just as engineered as the cellular glass itself. To execute something of this scale under a FIDIC Red Book contract, the employer needs absolute granular control over labor, over quality, and over measurement. The old saying goes, you cannot manage what you cannot measure.
And the labor hierarchy alone is staggering. The contract dictates a rigid workforce structure broken down into 7 specific labor categories, L1 to L7.
A literal army.
It really is. At the very top, you have the L1 superintendent overseeing the entire operation. Down the line, you have the L6 cladder, which is the skilled worker actually cutting the sheet metal and applying the weather sealants. And then, entirely separate from the installers, is the L7 quality control inspector.
And that separation of duties is vital. You absolutely cannot have the person installing the insulation also signing off on its quality.
Conflict of interest.
Huge conflict of interest. And that highly structured workforce operates under a system of ruthless mathematical efficiency when it comes to getting paid. The measurement matrix WBS-HI basically translates the physical chaos of a dirty construction site into a flawless accounting ledger.
But how does that actually work when the geometries are so wildly different? Like, a straight pipe is entirely different from a massive spherical storage tank.
It breaks down by spatial dimensions. So straight runs of piping are paid by the linear meter along the center line. It's a simple, verifiable distance.
Easy to measure.
Right. Valves and flange joints are paid by the exact discrete number installed. You count them, you pay for them. But when you get to the massive structures, the heat exchangers, the separation vessels, the LNG storage tanks, those are paid by the square meter of insulated surface area.
Okay.
So the contractor performs the work, the L7 inspector verifies the exact geometry, and the payment is calculated without any ambiguity.
And it also removes any ambiguity about what the contractor is actually responsible for, mostly through these really strict exclusions.
Yes, the do not do list.
Right. The text outlines exactly what the insulation contractor is not allowed to do. They don't apply fireproofing. They do not modify the structural steelwork to make their insulation fit better.
Definitely not.
They don't even paint or sandblast the pipes before insulating them. They are pure specialists. They just show up, confirm the pipe has been prepped by the painting contractor, and they apply the wrap.
This raises an important question, though. With all this specialization and all these highly specific rules about staggered joints and chloride-free materials, what happens when someone invariably makes a mistake?
Because humans are human.
Exactly. Say a tired L6 cladder misses a seam, or a layer of perlite gets slightly damp before it's sealed.
And as we established with the grain of salt earlier, the stakes are incredibly high. A damp seam means a cracked pipeline.
Right. So the contract leaves zero room for hiding those errors. The bureaucracy of quality control is as airtight as the physical weather sealants. Within 28 days of starting the contractor must submit a comprehensive inspection and test plan, an ITP.
Okay.
This document dictates mandatory hold points and witness points for every single stage of the build.
Meaning they physically cannot proceed to layer 2 until layer 1 is inspected. They can't just wrap a pipe, seal it in aluminum, and say, hey, trust me, the joints are staggered.
Absolutely not. The L7 quality control inspector must verify the first layer, check the material traceability to ensure it meets ASTM C533, and formally sign the documentation.
And if they find an issue?
If they find something wrong, if a joint isn't staggered or
Sure.
the material is compromised in any way, the process triggers an immediate halt. Any non-conforming work generates a non-conformance report, an NCR.
Yeah, and I imagine they can't just, keep that NCR internal.
Not under a FIDIC contract. The text mandates that the overarching engineer representing the employer must be notified of all NCRs within 24 hours of identification.
24 hours, wow.
Yeah. And then the contractor has to strip the faulty insulation, replace it with brand new material, and document the repair entirely at their own expense.
Ouch.
Yeah, there is an immense financial incentive to get it right the first time because rework destroys the contractor's profit margin. The entire system is designed to force total transparency.
It has to be, right? I mean, when you're dealing with 400 millimeters of insulation on a high-pressure line carrying process fluid at lethal temperatures, good enough is simply not an option. Every single millimeter matters.
It is a massive interwoven web of accountability. From the L1 superintendent looking at the master schedule, all the way down to the L6 cladder securing the final latch on a removable valve box, every single action is logged, measured, and verified against the initial submittals and the manufacturer's data sheets.
So what does this all mean? When you look at this dense, highly technical scope of work, it is really easy to see it as just a pile of administrative hurdles.
Oh, for sure, just paperwork.
Right. But it's actually a beautiful, highly orchestrated playbook. It proves that simply keeping a pipe hot in an industrial setting isn't just about wrapping it in a blanket. It requires this massive, multidisciplinary collision of forensic material science, thermodynamic physics, and absolutely airtight contract law.
SOWHI 001 essentially represents the invisible connective tissue of modern global industry. We rely on these massive energy systems, power plants, refineries, chemical processing facilities every single day to power our lives.
And we never really think about them.
Never. We never see the staggering complexity required to keep them operating safely. Without these meticulously staggered layers of cellular glass, without the nanoscale engineering of the microporous insulation, without that final 0.5 millimeter layer of aluminum cladding sealing out the rain, these facilities would succumb to thermal stress and literally tear themselves apart.
It it really makes you look at the industrial world differently. It isn't just brute force metal and fire. It is this incredibly delicate balance governed by chemical rules and legal frameworks we never usually get to see.
The scale of the engineering hidden just beneath the surface is truly remarkable.
Which brings us to our final thought for you to mull over today. The next time you are driving down the highway and you pass a massive industrial facility, a power plant, or a refinery, don't just look at the gleaming metal pipes and the towering steam stacks.
Look a little deeper.
Yeah, look past the surface. Think about the hidden layers beneath that metal skin, the tightly packed microscopic silica, the perfectly staggered seams, and the L6 cladders who meticulously sealed it all up just to protect the steel from a single grain of salt. And ask yourself, what other massive invisible systems are running the world around you right now, quietly governed by meticulous rulebooks you will never see?
See the link in the description for free PDF download. Also, watch our other construction scope videos. Thanks for watching, please subscribe, and see you next time.